You're working through a calculus problem when your progress completely grinds to a halt. The mechanism jams, and no force will push it forward. In advanced calculus, that wall often looks exactly like this double integral. Reading from the inside out, the immediate task is to evaluate the inner integral of sine y squared with respect to y. But the function sine y squared has no elementary antiderivative. Applying u substitution yields exactly zero progress, and integration by parts is entirely useless. You might be tempted to use a numerical approximation or a Taylor series to get close, but an exam requires the exact precise calculation. The roadblock here is not a lack of algebraic skill. The math hasn't failed, the perspective has. Treating this equation strictly as a sequence of algebraic operations is a trap. To solve it, we have to step away from pure algebra and translate the problem into physical space.
The terms dx and dy at the tail end of an integral define the physical orientation of the calculation. These differentials function as physical instructions. They dictate the exact direction we are meant to sweep across a geometric shape. This visualization shows the domain of a multiple integral. While the integral calculates a 3D volume underneath a wavy surface, the domain is a flat footprint on the grid. The limits of integration attached to our impossible equation map the borders of this exact footprint. According to Fubini's theorem, if we can accurately map out this two-dimensional boundary, we gain the ability to change the direction we slice through it. Cracking this integral depends on mapping its precise geometry. We start by isolating the inner limits of the integral. Here we see a clean coordinate plane. The lower bound of x translates to the diagonal line, y equals x. The upper bound translates to the horizontal ceiling line, y equals 1. Next, we look at the outer limits, which define the total horizontal width of our region. These limits tell us the shape spans from the y-axis, where x is 0, out to the vertical line x equals 1. When we combine these boundaries, the specific enclosed triangle is revealed. This shaded area represents the true physical domain of our equation. That intimidating algebraic wall is actually a set of instructions for calculating volume over a simple, flat triangle. To find our new bounds, we use the arrow and brush method to determine how we slice this region. The original problem integrated with respect to y first. This means an arrow shoots vertically through the triangle, entering the diagonal line and exiting the flat roof. The outer integral acts as a brush, sweeping this arrow from the left edge to the right. To change our order of integration to dx dy, we have to rotate our entire perspective 90 degrees. We execute the pivot by shooting a new arrow horizontally, moving from left to right. This gives us our new inner bounds. The horizontal arrow always enters the shape at x equals 0, and it always exits by hitting the diagonal line, x equals y. The new outer bounds are found by tracking the vertical sweep of this arrow. It sweeps from the floor at y equals 0 up to the ceiling at y equals 1. By rotating the arrow, we rewrote the boundaries without altering the physical shape, creating a sequence of operations that algebra can actually solve. We can now take these newly discovered geometric boundaries and snap them back into standard algebra. The critical difference here is that the inner integral is now evaluated with respect to x. Because we are operating in the x dimension, the entire term sine y squared is handled as a simple, unchanging constant. Integrating a constant with respect to x simply attaches an x to it. We then evaluate it from 0 to y. The result is a sudden y multiplying the front of the sine function. This specific algebraic artifact provides the missing derivative required for a standard u substitution. The physical geometry generated the precise algebraic piece required to move forward. We are now left with a straightforward single-variable integral to solve. Setting u to y squared means our derivative neatly cancels out the new y term we discovered. We evaluate the final step, integrating the sine function to produce negative cosine. We apply our final bounds of 0 and 1, arriving at the exact calculation. Representing the domain geometrically exposed a structural vulnerability in the problem, allowing us to generate the exact missing term the algebra required. Multivariable calculus relies on this link. The boundaries of the domain dictate the complexity of the algebra.